Excellent.
Excellent. I am also now live. Thank you, everyone, for tuning in. Tonight, we had a slight change of plans. I know it said we are going to be just reading about the tides, but we are actually going to be doing a quick little bit of research into ring laser gyros and inertial navigation systems. Alan is going to do a quick presentation here on the manual from an inertial navigation system. And yeah, there you go. Go ahead and take it away, Alan.
All right, cool. So this is the technical manual for the ring laser gyro navigator inertial navigation system, and then there's several different models that this technical manual covers. So we're going to read through here and get into how it works and all that. So this is the system right here. So what they do, this is a 3-axis gyro. So they have an x-axis, y-axis, and z-axis mount. So they cover all the orientations and they take average readings based off of that. And it's basically like a little supercomputer, and it has different components in it that are monitoring different aspects of the gyroscope. So when you get into it, really, like, this thing heats up, 'cause it's like a little computer. So they had to come up with some really interesting ways to counteract the like thermal expansion, for example. So we'll get into that. Um, so here we have the. So first of all, this device, they say it functions off the principles of the Sagnac effect. Now, but before we get into that, I didn't have time to put this in the presentation, but we'll just cover quickly what happens when you boot this device up, because a lot of people think that you just turn this bad boy on and it starts telling you that the Earth's spinning and all this stuff, right? So it's a little more complicated than that. When you first start the device, you have to input your relevant coordinate systems, lat long, based on whatever map references you need, and then it also takes input from GPS coordinates. So it takes a multitude of different points of data to put you on the coordinate, to get you reference, to put you on the coordinate system, to get your location on there. And then for 72 hours or for 48 hours, there's two different calibration links. They take multiple readings. Like, it just turns on and off. It just turns on and off over and over again, and it's just taking readings, and it's just calibrating its threshold. And while that's taking place, all of that, it's building a database basically through a bunch of different algorithms called the Kalman filter. And basically, the Kalman filter is a culmination of algorithms that serve various purposes that we'll get into as we continue on here. But basically, it's just averaging out the readings and how the device is functioning in reference to where it's at. So the whole time it's calibrating, it has to be stationary, and then it gets multiple inputs for reference, right? So that's how you get it calibrated to get it working. So you can get it to the point where you can, quote unquote, turn it on and it just knows where it's at and all these things. Well, it's like I said, like, the Kalman filter takes care of all that. It backs all that information up. It um, keeps it logged for reference. So when that does happen, and when they do a correction to the system like that, it's already backed up through the Kalman filter. So shout out to Kalman. All right, so we'll read the basic description here of the Sagnac effect that they give and how it relates to how they say they're measuring motion, right? Because a lot of people that work with these devices, they'll say, "Well, I work with these and it does the thing. Like, what's wrong? What's the problem here?" So we'll just read from the manual and see what they have to say about it.
Yeah.
So it says basic description of the ring laser gyro. Using light to measure rotation is based on the principle the principle that the speed of light is constant. The time required for the light beam to traverse a given distance is independent of the motion of the medium in which the light is traveling. For this reason, if the light were to travel around any circular path, the time required for to complete one revolution, 360-degree angular degrees, would be independent of the one way where whether the path be stationary or rotating. Okay, so he's saying that there's going to be a time difference between these. So, and we'll get into that with the absolute space here, but as an analogy for this effect, to measure rotation, suppose that the observer on the pathway emits two beams of light in opposite direction and then measures the time required for each beam to complete the revolution and return to the observer's position. If the pathway is stationary, both beams would be received or would be back or would be received back when the observer's position is at the same time. This condition is shown in figure 4, and we'll get into that here in a second. If the pathway is rotating, however, one moves towards the beam and away from the beam, and while the beams are traversing the path, while the beam is traversing the path. So they're invoking a distance change there within it. Hold on 1 second. Okay. Sorry. All right. If the pathway is rotating in the same direction as the light beam, then the path length on the observer is effectively lengthened, right? So this is how they're explaining it. Convert in the confines of special relativity, right? Because they don't even get into the general relativity explanation, which is like canon. So conversely, if the pathway was rotating in the direction of the opposite to the light beam, then the path length would be effectively shortened. The time difference between the reception of the two beams would measure of the rate in which the path is rotating at a sequence in which the beams would receive is indicated in the direction of rotation. The rotation is included in the difference in the path length that is referred to the Sagnac effect. So this is what they're teaching people about the Sagnac effect and how it relates to general relativity in this manual here. So the issue here is that they're invoking absolute space to change the time to invoke a time difference for the length traveled, and that's explicitly against the principles of special relativity that we're going to get into here in a second. All right, so from Einstein's 1905 paper, he says here, we will raise to the conjecture, the purport, which we will
Alan,
hereafter call the
I only
principle.
see your we're still on the first frame here on our end.
Oh, no way. Hold on.
Oh,
How about now?
yeah, that
Yeah.
works.
Oh, my bad. It's because I minimized it. So sorry, guys.
All good.
So
How many frames
sorry.
did we miss?
No worries. We're about to go back and check them all.
Cool.
It was just a couple.
Yeah, it didn't. I
Good.
was kind of curious. I almost said something sooner, but then
I thought he was reading from memory from the notes, and he was going to transition to it. Honestly,
yeah, same.
Well, I mean, a lot of it was, but so we got here. This is the title for the manual, the cover page. Is it updating now? It's not updating on OBS now. Hold on. One second.
second slide.
Okay. So we should be on that. Nope. Come on, man. All right, whatever. I got to do it like this for the YouTube. Okay. So you guys can see it though on your end correctly, right?
Yeah,
Is it updating slides properly?
still on the second one.
Nope. Okay, that's no.
Okay, intro.
All right, one second. All right, what do you got now?
Still the intro. Oh! I
There
see
you
moving
go.
slides.
Whoa.
All right. We got a movie slide. I like that. What about now?
Front view, door open, cover removed. It didn't change when you said "What about now?"
Sick, dude. Not. Oh, Okay, hold on. I know what the issue is. It has to be running the background on the side. How about now?
We see you going through your slides.
Second.
Yeah, I think it's good now.
Good now? Okay, cool. Let me make sure it's good on YouTube. And now that I know. Okay, yep, it looks like it is. Roll. Okay, and then you guys are seeing it too?
Yep.
Well, first one.
Awesome. Okay, sorry about that. Okay. All right, we're back. Okay, so this is the technical manual here, and this serves for several different types of navigation systems. This is the system itself. It's basically a computer, has 3 gyroscopes mounted on it in different orientations for the X, Y, and Z axes, respectively. And then we were getting into the explanation that they give in the manual for how the Sagnac effect works. So basically what they're setting up for is an analogy to describe a time difference between an observer that is stationary and an observer that is in rotation. Now, they're saying that the rotating observer there will be a time difference between him and the stationary observer, and that time difference relates to the velocity of rotation of that observer. So they're saying that they could measure that time difference and get a velocity. Now, you can measure a difference and get a velocity, but the mechanism is different for how it actually works. Because they can't, because this technology actually falsifies special relativity's principles on the face of it. So let's see, where we left off was they were invoking absolute space to explain the distance change, right? So they were saying that that for the stationary observer and for the rotating observer, the one's travel time will be different than the other's travel time. So we'll get into what that means exactly here. All right. So before we continue, though, we have to preface on why this is important for special relativity and why this is such a big deal. So we'll read from Einstein's 1905 paper. We raised with this conjecture to purport hereafter call the principle of relativity, that we were going to raise this to a postulate and then introduce another postulate, which is apparently a postulate, and then introduce another reconciliable from the former, namely that light always propagates in empty space with a definite velocity of c and is independent of the state of motion of the emitting body. These two postulates will obtain or suffice to obtain a simple and consistent theory of electrodynamics of moving bodies based on Maxwell's theory for stationary bodies. The introduction of a luminiferous ether will prove to be superfluous, as insomuch as the view here will be developed will not require an absolute stationary space to provided with special properties, nor assign a velocity vector to a point of empty space in which electromagnetic processes take place. So the difference in the setup here, invoking the two reference frame transformations between the stationary observer at the center of the rotating device and an observer where the photographic recorder is placed, the time difference there that they're trying to evoke isn't valid because Einstein's explicitly saying that you can explain his theory without doing this, right? And then he further goes on to say that any uniformly rotating platform, is considered an inertial reference frame, because if you extend any part of it to infinity, it's basically linear. So his equations should hold true. So this device that rotates in uniform rotation shouldn't produce a fringe shift pattern to measure angular rotation, right? Because the actual measurement comes from the physical fringe shift pattern displacement that comes from the variance in the speed of light. So they're trying to invoke the variance as a reference frame time difference. And that's actually not sufficient to even explain it. So we're going to get into what that is here. So this is a guy named Pognier breaking down in 1926, breaking down the Sagnac effect with a rotating interferometer. I think the diameter is listed, or the rotation rate's listed on here. Yeah, 20 meters a second was the rotation, and special relativity can't explain this. It can't explain the physical fringe displacement based on the way that it tries to do it with the gamma factor correction, right? So aboard the traveling uniform platform, you're going to get your gamma factor correction, blah, 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 and it's based off of velocity, and you're going to get the time difference with the stationary observer. So they invoke that geometrically convenient position where they have an observer at the center watching the rotation, and then the other guy that's on the rotating platform, there's where your time difference comes from, right? So this prediction, this way to explain the effect within relativistic confines was off by more than 30 million. Given that velocity ratio,
just a little 30 million.
Yeah, a little off.
Yeah, and keep in mind, like the importance of that is like these measurements of velocity that come out of this machine are based on fringe displacements that are caused by a difference in the speed of light going in opposite directions, not from a change in the path length of propagation, in the sense that the mirror is rotating away from the propagation and then rotating into it. And the reason for that is that the time that the prediction is made in the lab frame, right, using the equations that describe an exact amount of distance, an exact amount of rotational speed. So if those were to change or be different, then they couldn't make the same prediction. So on the rotating platform, those equations make the same prediction. So the time is the same, the distance is the same. There's no change just because it's in rotation. So invoking absolute space to then say, okay, well, let's do a transformation to explain this is completely inadequate and exactly what Einstein said that he could do without.
That's
All right,
just what they
so
always try to do. So
yeah, and then this also ties into the Michelson-Gale-Pearson experiment, where they actually reverse the fringe shift pattern prediction for relativity, where there would be no fringe, and they said that there would be a fringe, and they made the ether prediction that the ether would get stuck in the pipes, and it would cancel out the effect due to Earth's quote unquote Earth's rotation, right? So they have so whenever they need to adjust the theory to make it fit, they just invoke whatever they need to, and you know special relativity can't explain Michelson-Gale-Pearson either, because the explanation that they give to try and explain it without invoking absolute space is that Earth's magnetic field drags the light with it in rotation, and that's what causes it. And because there's no north-south difference in the fringe shift patterns, that can't be the case, because those would have to be physically displaced as well, like the north-south. So that can't be the mechanism to even explain it. They just kind of bury it, don't really talk about it. And they tell you that, yeah, it was done within the confines of relativity's predictions, but it was done, relativity was changed to conform to that, and then everyone was just told that it's proof of it. So very cool. All right, so let me make sure I didn't miss anything here on the notes. Pognier, time difference, stationary, absolute space. Yeah, we're good. All right. So
This beautiful
so
image, so pretty.
yeah. So to explain the Sagnac effect, to kind of go over that and give give a visual for it, they made this awesome graph here where O is the world
It
line
literally,
of the station
just
of
to
the
be
stationary
clear,
observer.
it literally makes me sick to my stomach. This image.
Yeah. So this line that's deviating here is the observer that's in rotation. So his timeline is deviating from the stationary observer's timeline based on the 2 pi r. So this is the angular distribution, or I'm sorry, this is the distribution of rotation based on the area of the device. And then anyway, what they do to explain it is they have to put in a stationary observer in the center of the device. So this is your boy O, and then the deviation is from their rotating position. That's how they invoke it. And then this can't even explain it, because again, if the speed of light is the same, it doesn't matter if the rotation if the mirror path length changes in one direction or the other, because when it combines, it's going to be in phase again if it's the same speed, and it's not going to produce an actual fringe shift pattern. It couldn't possibly produce one. And they even state this in this paper, and they're like, okay, well, but since we already set you guys up for a geometrically convenient position, we'll go ahead and explain it through these confines. And then they offer no actual explanation for the fringe shift pattern. At best, they could only explain a second order Doppler shift that's proportional to the velocity of the rotating platform, but they couldn't explain the fringe shift pattern. So we'll move on to this is just from their paper too, but we already explained it. So this is from Barada's paper that's as late as 2022, where they're still trying to explain the Sagnac effect and give commentary on it. And they're like, hey, that old rotating platform and that guy Ruyang Wang in 2004 that linearized the Sagnac effect and showed that it can actually measure linear motion as well, and it doesn't really matter. Literally same equation. Remember that guy? So we got a problem here. So we'll just go ahead and try and explain this with the thought experiment. What's our thought experiment entail? And invoking the midpoint of the device to invoke a geometrically convenient space to preserve absolute space, so he could say that the distance of the linear path traveled, blah 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 blah.
Yes.
Right? Same old, but no possible mechanism to explain the fringe. And they even go on to say here, in the case of the relative velocity between the detector and the reflector, the distance between the detector and the reflector continuously alters, unlike the Sagnac experiment, where the distances always remain the same as in the lab frame. In the thought experiment, original Sagnac kind of experiment involving rotation also violates the midpoint measurement as the root cause of the Sagnac effect in the lab frame. So they got nothing to explain this, man. Not a single thing. And they even go on to say some worse stuff in their some more they're like explaining the physical fringe is, extremely difficult with our theory. But here we go. Like, anyway, were you going to say something, Shane?
Yeah, well, that's exactly what they try to do. Like they have nothing to do, but what they do is they try to apply those relativistic corrections secondhand with no explanation, and then say that everything's fine.
Yeah, they show you the math, and then they hope that you're good to go on the explanation.
That's what they do.
Even though by Einstein's own postulates and what he says in his paper about a closed polygonal circuit in uniform rotation, and how his equations have to hold true in there because Newton's equations hold true in there. So, and he's covariant with Newton, right? The whole thing is based off of covariance and backwards compatibility and all that. So it would have to be the same, but it's not. So here is the diagram that they give to explain the Sagnac effect in the manual here. Just the simple Sagnac setup here. They're saying that the A observer is stationary, so there's no delta t, no change in time. Then they got their moving observer on the edge of the platform where the light ring is going around the platform. So they're saying that that's a moving observer, so he has a delta t. Then they combine the two, and then they count the nodes in between that time difference of the quote unquote stationary observer and the rotating observer, even though their time is actually the same. And this is all a ruse to get you to not realize that the physical fringe displacement is the biggest false relativity manual here. This lately in technical velocity of the Earth going through it. Yes, sir.
Sorry, is he roboting for anybody else, or is it just
Hard,
me?
yeah, roboting hard.
Okay, 1 second.
Yeah, for like the last, I would say about 15 seconds, 20 seconds.
Nope, no worries. Let me check YouTube. Yo, am I roboting, lads, or is it just on Discord?
Sounds
Audio
good
check.
now. You're not
Testing.
roboting on Discord anymore.
Roboting specific to Discord, just so you know.
Okay, cool. Just wanted to make sure. Just want to make sure it wasn't the internet.
Doesn't
you know
happen
how that
anywhere,
goes.
as far as I know.
Yeah. All right. So these are just some things I thought were interesting that were in the manual. So we're going to go over these now on the functionality of the gyro and like how it works, right? So this is from the gas. No, this isn't from the gas flow. This is from explaining how it works. So this is the pathway consists of a sealed channel which is filled with a mixture of gases that emit light when ionized. The voltage applies to an electrode, and in this channel ionizes the gas and causes the lasing action. So this is producing the laser, like the gas, the interaction of the ionizing of the gas inside is producing the laser. When the ring is stationary, the lasing generates a standing light wave, which is analogous to two counter-propagating light beams. So this is what's generating the counter-propagating light beams. The interference between the beams, blah, blah, blah. Dang, why did that not turn out right? Related to next slide. Oh, okay. Well, anyway, so this process here of the lasing using the gas and all that, right? This creates a laminar flow inside of the sealed chamber of the gas, right? So here's what they say about the gas flow and how they correct for this laminar flow that creates Fresnel drag, which creates an additional velocity boost to the speed of light that they have to account for in the calibration to make sure that this device actually is measuring motion and not the other etheric effects related to motion. Okay, so gas flow. In an idealized gyro, the standing wave generated in a light beam would remain stationary when the light path is not rotating. In actual practice, the flow of the ionized gas inside the ring produced by the bias which causes the effect which causes the standing wave to rotate even when the device is stationary. The gas of the flow is a result of the high voltage between the cathodes used in the ionization of the gas. Electrons in the gas would shift towards the positive anode and the positive ions shift towards the negative cathode. This introduces a net flow of neutral atoms in the gas around the ring. To compensate for this effect, a balancing ionization circuit is used in which consists of one cathode and two evenly spaced anodes placed on the opposite sides of the rings. So they're basically just creating another flow of electricity so they can hit it with a opposite flow of direction for the high to low pressure mediation. So by measuring the current in each ionization path and controlling for the ionization voltage, the counter propagating motions in the electrons in ions can be established, which cancel out the flow of the gas ring. So Fresnel drag was the concept that material media would its molecular structure would drag the ether along with it, so giving it an additional velocity boost as the ether moves through it, and then as electromagnetic propagation moves through that would catch a boost essentially from the total velocity, that total translational speed of the moving media. So to test this, who was it? Fazal took split a beam of sunlight with a mirror into basically an early interferometer that had a flow of water going through it, where the beams would go with and against the flow. And what he found was, after accounting for refraction, there was still an additional 44% velocity component going with and against the flow of water that produced a fringe shift pattern. And this was actually the first measurement made of velocity using a fringe shift pattern, where they deduced that proportional velocity relationship using the fringe, and they deduced that the speed of the moving water contributed to 88% of the fringe shift pattern. All right, was that about right, Toby?
Yeah, Fresnel, Fizeau. It was Fresnel's math, Fresnel's math, and then Fizeau did the experiment. But yeah, that was pretty much all right.
Yeah, so this idea of Fresnel drag, this ether component with the moving media. So what they're saying is that in the gyro, the high to low pressure mediation induced to create the laser beam to ionize the gas creates a flow, a laminar flow of gas within the tube, which also drags the ether with it, which produces an additional velocity component that has to be reduced in the Kalman filter. Well, actually, they don't Kalman filter it. They account for it with the what do they call it? The ionization circuits. So they got two other additional anodes on each side of the sealed chamber or sealed channels, and they're basically inducing their own current flow to counteract that current flow that's caused by the ionization in the first place. So that's cool. Just canceling out the old ether effect, Turns out the ether doesn't get trapped in the tube and cancels out rotational effects or whatever they said in Michelson Gale.
Originally
turns out they explicitly have to account for the ether in the gyro itself. Very cool. All right, so and the lasing action. Let's see. It causes the lasing action when this was supposed to be part of the other one. I see what happened now. Okay, when the ring is stationary, the lasing in the ring generates a standing wave, which is analogous to two counter-propagating beams. The interference between the beams generates a series of nodes, stationary points. So they're describing how the fringe shift is measured here, basically. Sorry, this was supposed to go up earlier to describe how they're actually measuring the fringe. I apologize. This was supposed to give you full context on the fringe shift pattern relationship and velocity. Okay, so when the ring is stationary, the lasing ring generates a standing light wave, which is analogous to two counterpropagating light beams. The interference between the beams generates a series of nodes, which fringe shift patterns, stationary points or minimum points of minimum intensity, and the node points of maximum oscillation, as shown in the left figure 13, which is the one I showed you guys earlier. Because of the frequency of the laser is very high, more than 1 million nodes and antinodes are generated in the path in less than half of a meter in circumference. So you guys went over the data and saw what was the readings per second? It's insane. Like just what they put out on the raw data from Bob's measurements when they had the gyro. I mean, this thing, it's not
like 0.000. Like I can't even remember how many zeros per.
Yeah, if you could
per second or whatever. Yeah.
Yeah, if you could go over real quick, like the intricacies of what it's measuring, because you said it really nicely recently, where it was like relative to what, like the temperature, the barometric pressure, like all these things have to be accounted for and zeroed out, and it's like how much of this is being, how much of these effects are being canceled out to make it hit the 15 degrees per hour, because clearly this thing doesn't hit 15 degrees per hour just like a magic number threshold. right? It goes over that, and then they have to bring it back down for various corrections. So we're going through the process and the corrections and the measurements and how all this works, and we're finding like, well, it's not as simple as like you just plug this bad boy in and it's 15 degrees per hour. They've got a set rate for what they need to hit. They've got algorithms on how to get there to make sure that those readings will keep you specifically in tune with their coordinate system while you're operating on another coordinate system on the back end that's telling you that you're really using the true coordinate system. So there's a lot to consider in what they can do with these devices, in that margin of error in the readings that they bring back down to a 15 degree. Was there anything you wanted to add to that?
No, well said.
Cool. Okay, so we'll move on from this because this was just the explanation given for the fringes, but we kind of already went over that a couple of times. So this is Wang in 2004 with the linearization of the Sagnac effect. And if you see the equation here, delta T equals 4 omega A over C squared times, lambda, right? And the other one's the C squared too. But it's not on there. But anyway, the effect of linear motion, like the equations are the exact same. They both make the same predictions, and they're both in Wang showed that you could measure linear motion with respect to, absolute space, right? So the thing that they say can't be done, doesn't exist. Otherwise, Michelson-Morley would be incorrect, right? Because Michelson-Morley was an attempt to measure linear motion, but all they picked up was a fluctuation that matches sidereal time. Well, that was later corroborated by Miller. But like their measurements didn't even give a constant speed for C. So like the whole basis of like we can't measure linear motion, speed of light's constant. When you take it back to even Michelson-Morley, they still have they still got a fringe shift pattern that corresponded to an actual velocity component of 6 kilometers a second, and that was later confirmed by Miller and Galev and some other people with these fluctuations and all that. But the idea that you can't measure linear motion and all that, like that's over, man. So we got the equations to represent it all, to measure it out. They're all equal. They all predict the same thing in both reference frames, in the lab frame and in the quote unquote rotating frame of the apparatus. All right, so we'll get into this thing called frequency locking now. And this is where they basically what happens is when the device is stationary, there's like some of the light goes through the mirrors and it reflects back, so it causes the waves to go out of phase when they're when the angle of incidence is 180 degrees from it. So it's just bouncing back and it's just messing with their readings, right? So what they have to do to fix that and stop that from happening is they vibrate the device back and forth in a process called dithering. So they're just rapidly vibrating this thing to induce a phase shift in it, and then they cancel out that phase shift from the vibration, like with the signal processing from the Kalman filter. So they induce a phase shift so that they don't get the signal locking, which will just interfere with the readings when it's not in motion. And then they have the path length control, which I thought was really interesting. And I hope Pizzo's here to hear this because this is awesome. So the intensity of the laser beam is dependent on the spacing of the reflective surfaces as a multiple of the wavelength of light. Ideally, if the position of the mirror surfaces in the laser could be fixed so that the length of the lasing path was held constant at the exactly some multiple of the wavelength. I keep wanting to say multiply of the wavelength of light, the laser would operate at a maximum efficiency and intensity. Stability of the laser length and the path length is maintained primarily by use of a material of the laser, which has a low coefficient for thermal expansion. In addition, the ring laser gyro in the ring laser gyro dynamic mirror positioning system, known as the path link control system, the PCL, adjust the path link. In this design, 2 mirrors are mounted on piezoelectric transducers which allow them to be moved inward or outward to adjust the path length. So circuits in the system are constantly monitoring the laser intensity and apply a bias voltage to the piezoelectric transducers, which position the mirrors to maintain the maximum intensity. So when the piezoelectric material gets charged, it physically deforms, so it expands, and like they use that expansion to adjust the mirror to move it back and forth when the device itself expands, due to just how it's running, right? Because it's a literal computer system. So there's going to be expansion in it, and with measurements these fine, every little bit keeps contributes to that. So I just thought that was really cool that they do that. So when they discharge the crystal, that deformation dissipates. So they literally move it back and forth by inducing an electric current through the piezoelectric transducers. Very cool use of piezoelectric material. And I think I've said piezoelectric enough times. Yeah, piezoelectric.
Shout out Piezo.
Shout out to our boy Piezo. All right, so let's see. I think that was all I needed. Oh yeah, so really interesting on that. So some people will say, so the general relativity explanation for the Sagnac effect, by the way. So this is the actual explanation that they give for the Sagnac effect, because as we went over, there's no time difference in the special relativity derivation, and it's inadequate actually to even explain a physical fringe to begin with from their paradigm. So Paul Levoux had to come in and say, well, boys, it's a rotating device, so we got to treat that as an acceleration. So we can invoke general relativity, use the equivalence principle to say that rotation is equivalent to a gravitational field. We can conserve the momentum and energy of the rotation in that gravitational field and say that generates temporal pockets of time dilation and length contraction, so that we can actually explain the physical displacement of the light beam, so that it produces a fringe shift pattern that's proportional to the velocity. So that's how they wrapped all that up with general relativity. Instead, they treat the rotating platform as a non-inertial frame, even though it's explicitly detailed in Einstein's paper that it is. They say, no, let's hit up your boy general relativity. But these corrections that this technology, how it works, let's say there is some length contraction, time dilating going on. They're explicitly changing it back. And making it not contract,
sinking it back to absolute time.
Yeah, dude, they're actually changing the physical contraction mechanism back. So that's actually not even a real thing to explain anything anymore. If anyone wants to tell you that if anyone actually gives you the Paul Levoux explanation, you can tell them that a inertial navigation system has piezoelectric transducers in it that account for any sort of quote unquote expansion or contraction, which is actually related to thermal effects, right? And not due to the mysticism of space-time contraction. So I thought that was really cool that they did that.
But good point.
Yeah, I'm glad we did this, man.
Yeah, shout out to that guy you had that conversation with, because I was like, you know what? I've been itching to read this manual and give it a good thorough rundown.
I can tell from my uncomfortability that I should have read this before. That's okay. It's all right.
Yeah, it's all good. So we're about to get into the really interesting part of the polar coordinate and the true coordinate system. So this is the statistical before we get into that, though, we'll touch on the Kalman filter. So that Kalman filter that I was telling you guys about earlier, we're going to touch on that now. There was a lot of text to go over, so I just summarized it and broke it down. So we'll go over the key points of that. So the Kalman algorithm constructs a reference database using a specific set of parameters and coefficients to efficiently manage all aspects of the output readings. It achieves this by comparing the device against information within the algorithm. So it has a reference, and then it takes readings. It starts a database. It starts cross-referencing that as it's narrowing down the effects and what it needs to calculate, what it needs to attribute, what all the piezoelectric crystals need to do to fix everything, right? Your boy Kalman is fixing all that. And then when this device goes out of sync or for various reasons, because they actually have a drift rate that messes with them apparently, that's outside of the confines of whatever. So they have to kind of reset it sometimes and use old data points. And this was really inconvenient. So this guy Kalman stepped in it came up with this way, like an algorithm to kind of keep track of everything. So when you go for these position resets and everything, it seamlessly pulls it all back together. And then especially that comes in handy when we get into the true coordinate system and the polar coordinate system, because the seamlessness between these two coordinate systems is actually entirely facilitated by algorithms made by your boy Kalman. Okay, so let's see. The inertial navigator deploys the physical reference to drift rates over time. Let's see. Okay. So the three fix reset technique. So the three reset fix technique was in regards to when the gyro gets out of sync with that drift rate. They can do resets within 24 hours of calibration and make all the necessary corrections that they need to. But the problem with that is if there's any errors in those corrections, then the whole system's off again, and they have to start the calibration process again. So Kalman kind of came up with like a system restore point where they could fix that, so they don't have to like really use that method anymore. The Kalman just kind of seamlessly transitions them back whenever they need it. Very cool. All right. So the concept of optimum estimation of the revolution of the platform made of the compensates. Okay. So it's just going over error correction. So like I said, it's basically the brains behind it's the processing unit behind all these data points that this thing measures, and it figures out what needs to go where essentially, right?
I think. Oh, there we go.
Yeah. Go ahead. Did you?
I thought we lost sync with your slides, but we're good.
Okay. Okay, cool. So we have operating in polar mode. So now we're going to get into polar mode or they call it traverse mode and their true coordinate system mode. So operating in polar mode. At a high latitude, the ring laser gyro operates in traverse coordinate system polar mode. 1 second, I have to clear my throat. Okay, yeah. So when they pass the 86th latitude, the system automatically switches to polar mode. And when they go below the 84th, it switches back to true coordinate system mode, which is how you know that the true coordinate system mode that they use all the time is definitely the true one. Okay, so when they go into polar mode, a series of algorithms from the Kalman filter is activated. So there's the strap down computations, which remain. Oh, actually, I break each one of them down. So we'll get into each one of these components specifically and talk about what they do and how they relate to the two different coordinate systems and keeping them in sync. So like this idea that we kind of put forward in Flat Earth is like, yeah, there must be like a hidden map. They're hiding distances, they're changing things, and they're like, well, I got an inertial navigation system, and I got on a plane, and the plane took me to where I'm going, and the globe is they're all referenced the globe, so I don't know. And that's a fair point, man. Honestly, dude, if I got in a plane and it took me where it said it was going on a globe, I'd be like, well, goddamn, it's a globe, right? But let's look into this system explicitly works off of a mechanism that would be that you could use to spoof that, right? To have your position referenced on an actual coordinate system, and then have it running parallel to the fake coordinate system, and have everything aligned, like your velocity, your position in 3D space, everything be in exact alignment with that other coordinate system. So these are the exact mechanisms for it. This piece of technology explicitly works off of that. It's not like out of the question that, oh, that could never be done. They'd all have to be in on it. It's already in the technology. It already works that way. It's already built in. They already did it. They were already in on it. How about that? If there was anyone to be in on anything, right? So anyway, the strap down computation maintain altitude, direction, cosine matrix relative to the transverse frame. So what they're doing in the true coordinate system, that's basically taking the snapshot there, and it's creating a cosine matrix to relate their position of speed, velocity, their coordinates, everything, all their motion, like their vector, bearing, heading, everything about that ship and where it's. Or I always picture these things in a ship, so that's where I go to when I talk about it. But anywhere that this whatever this apparatus is attached to, it's going to mirror that on the polar coordinate system, right? So the direction cosine matrix is used to determine angles of the axis of one coordinate system to another, In the context of the inertial navigation system, it would specifically involve representing the relationship between the axis of the polar coordinate system and the axis of the true coordinate system. This allows for the transformation of the computational operations between the two systems to be seamless. This is the baseline of how the inertial navigation system can be navigating with respect to another coordinate system without you knowing. 1 second, got a text message. Check email for code. 1 second, gotta send out the code. 1 second, I do apologize.
All good.
But yeah, we're about to read multiple iterations of this basically. So I'll make the this next section quick here because they're all what I just summarized is basically just the different algorithms that they use to apply for like velocity, position, et cetera, to mirror them between the two. So 1 second, I'm just waiting for an email confirmation code to give to my mom.
A few of those items on that list looked pretty interesting, for sure.
Yeah. All right, so we'll continue on here. So the next algorithm that gets triggered when polar navigation mode is activated is the Euler angle extraction. This extraction of this matrix yields the roll, pitch, and polar headings. So the extraction of the roll, pitch, and polar heading angles of the direction cosine matrix provides the system's orientation in three-dimensional space and provides the relative position for both coordinate systems, normal and polar. This information is essential for accurately determining the system's spatial orientation and location on both coordinate systems. To maintain your orientation, so to summarize, it's to maintain your orientation and position on both coordinate systems so that when they need to, when they need to switch it back, you'll just seamlessly think that you never left the place. All right, so we have 3. Accelerometer outputs are transformed by traverse DC matrix yielding traverse coordinates accelerations. So the accelerometer outputs, which represent the system's accelerations, are transformed using traverse polar direction cosine matrix. This transformation will result in the representation of accelerations in the traverse coordinate system. So they're taking the movement from the true coordinate system and applying it to the polar coordinate system to make sure that they're in alignment so that you don't accidentally get lost or, navigating on the two different coordinate systems. Because if they're going to like change distances or have different references for certain locations on things, well, they have to have a spot where they put everything, right? Like there has to be actual locations. So when you have people navigating through these areas where there's going to be discrepancies, you're going to need them to go to navigate, where you want them to be, right? So you're going to give them specific coordinates to follow and to make everything match proportionally because they don't in reality. Right, they have 2 separate systems that they give you, and this is just basically mirroring everything and keeping it seamlessly so that you don't ever ask questions or think about it.
Avoiding that old globe drift, huh?
The old globular drift. So 4, traverse accelerations are integrated to yield traverse velocities. So the accelerations are measured in traverse coordinate systems are mathematically integrated to provide corresponding velocities in the same coordinate system. Essentially, it involves accumulating the traverse accelerations over time to derive the polar velocities. So it's just basically measuring, it's just honing in the accuracy of the velocities of the measured velocity so that it can keep those coordinate systems intact, right? And then we got another one doing the same thing, tracks your relative velocity between the two coordinate systems, and then it this one actually compares the lat long and then makes corrections based on that to keep you going. Shane, you're familiar with lat long corrections. When you see a lat long correction on a coordinate system involving, military technology and, geoidal reference systems, like what are your thoughts on that?
Well, I immediately think that they've already translated it to a spherical coordinate system and that no one who's working in that data set would think to translate it back, but,
So hidden in the transformation, very David Copperfield or whatever that guy's name is.
No, it's more like that math trick where they like equate 1 to 3 and then do some algebra, and you're like, whoa, and you're like, but we started with a false premise. Tricked you.
Oh, a Lorentz transformation.
Right.
Yeah. So,
Hey,
okay,
our campus here. Sorry, I came in late.
1 second. Let's say we have number 6 here. So, Earth rates, transport rates are obtained. So basically, again, this is just keeping everything in alignment with the velocity stuff. Then 7, we have the Cowan filter operates in traverse and coordinates positions to fix resets. So it's just backs up everything in regards to if they have to do like a reset for the drifts or whatever. How they had to do that was it the 3 set fixed position thing or reset or whatever, so they don't have to have any problems with that. It'll always back up to the to the relevant spot on the reference geoid. So we have number 8 now. True coordinates are derived for display purposes. So after all that computation on the back end, the last piece of algorithmic aid that's given to us by Kalman is we get to see our location on the true coordinate system. So it gives your location on your reference ellipsoid of your choosing.
Your favorite ellipsoid, spheroid model, whichever one you want to choose.
All right.
So these things prove globularity. But why are we programming globularity in them first, though?
Yeah. Great questions. Great questions. All right. I have to go AFK for a second.
I think there was a contention when we did this before. They were like, nah, it doesn't know the latitude, longitude. And the actual answer is it only needs your latitude. It doesn't care about your longitude because everything, of course, is latitude dependent.
Yeah. I mean,
It's
it
the
corrects to
gyro
both.
compass you're talking about.
What's that, SC?
What's up, man?
Yo, what's up, guys? I was wondering, are you guys talking gyro compass? I just came in. What are you talking about?
Yep. That is the topic for the night.
Ring laser gyros. And
Nice.
fiber optic gyros.
Good stuff. Good stuff.
Although next should be gyro compass because of them dudes in your room, man.
I'll be right back.
Right? Learn some stuff and then you practice and you're like, oh, you know what? I need to learn some more. Hold on.
You guys ever tackle the mechanical gyro compass?
Nope.
That's an interesting one.
What do you think about that?
Well, from what I looked at, because they claim that it automatically searches north when you spin
Right.
it up. Yeah, that's a bunch of bull. After you spin it out. Yeah. The mechanical gyro compass, right? If you spin it up, let's say you spin it up and you get it up to the desired RPM, you can make it point east, for example, all day long.
Oh, that thing. Yeah, no, I've seen that before. That's the
Yeah.
one where they were like, "Oh, it processed a little bit on its own. It's going real fast." Like, okay, is that supposed to emulate? No, that's nonsense.
Yeah, I'm talking about a gyro compass, right? Not a gyroscope, a mechanical gyro compass.
Yeah, this is what Eggshell was
Yeah.
yelling at me all night about.
Yeah, they're full of it. Yeah. So just for like talking points, right? A mechanical gyro compass can be made to point in any cardinal direction. So the fact that they say they spin it up and it finds north on its own, that's not true. There's a whole bunch of weights on it and a whole bunch of things that make it point north.
Weights.
Yeah.
You don't enter any. It's not digital, so.
Yeah, think about it, right? You got a gyroscope, right? You spin it up. Does it point north? No.
Why the hell would it? Yeah, hold on.
Yeah. So why would a gyro compass point north? Why? It's just a gyroscope.
With a compass.
Yeah.
Because of the compass part, I would presume.
Yeah.
That's just so weird because it is one of those things that like they enter the knowing that like they get told that it proves it. The instruction manual says that it proves it, the video saying that it proves it. You don't actually see one like proving it. You're like, I don't actually determine the mechanism that's pointing that north, but you're telling me it's Earth spin? Okay. All right.
Yeah, think about it. A gyroscope, when you touch it, right? It processes right hand rule 90 degrees, right? So why would it point north? Think about it. Why would something that is designed to keep rigidity in space, why would that thing point north on its own when you spin it?
Right? But then why would that be their biggest weapon, prepared, ready, locked, and loaded? We have the gyro
Because,
compass. Like,
yeah, because they think we're not going to look into it, right?
yeah, you're probably
Just
right.
like you guys with the satellites, right? Time dilation. Yeah, sure. Then a couple of boys read a couple of papers, and what happens, right?
Gone. Well, you know what?
Gone.
You can believe in little pockets of space time that swirl out whenever you need them to protect globularity, but the rest of us will be back in reality. Thank you very much.
Yeah.
Yeah, UPS is a fun one. But Jesse knows just enough to like muddy the water for anyone who's listening who doesn't quite know, so that the like taints the neutral observer. That's what I realized when he was talking. I was like, you're not really saying anything, but if any Globers are listening, they're gonna be confused, and that's your goal.
Yeah, all they need to do is reassert themselves with a lot of confidence and gaslight you, and like it doesn't matter if there's like no substance behind what they're saying to someone that's not
Yep.
trying to, follow along. They're just going to assume it was a wash or that the more confident person was right.
Yep, that's right.
Yep. Exactly.
So nuh-uh. I get it.
Hardcore, nah,
Yeah.
yeah.
Like, yeah, what is the globe's claim about the gyro compass automatically finding north? What do they say is the mechanism that allows for this to happen? And furthermore, how is that reliant upon a globe in order for that to take place?
Earth rotation. That's their claim. So the only claim that they can make, because a gyroscope, in order for it to process, has to be moved, right? And it goes by the right hand rule. So you touch it, it moves 90 degrees, right? That's what happens. So
That's way too short and concise to be a proper globe response. That has to take at least 15 minutes to say.
I'm sorry, bro. I'll make it longer next time. Yeah. So yeah, that's basically it. A gyroscope has certain properties, right? The main one is it keeps its rigidity in space. So there's no way to convince me that if you spin a gyroscope and you call it a gyro compass, it's going to find north on its own. That just can't happen.
But they repeat
I
it
feel
an
like a
awful lot.
process like that would take an extended period of time to actually happen if that was a legitimate cause to this gyro compass supposedly finding north automatically.
Yeah.
If you needed to find north, doesn't a compass do a good enough job of that? Just saying.
That was my first reaction. Hey, does my gyro compass point north? Is that the compass part then, or like?
Well,
Well, there's a legit explanation for that one,
Okay.
because
Yeah.
you wanna go, Napalm?
No, I was just gonna say it's magnetic, and the other would have to do with the spin. So it could give a fuck all about like magnetic declination. So that would be interesting. I would be interested to see a test of these areas in which they have large magnetic declination discrepancies, and navigating them with a regular compass and a gyro compass, and see, kind of put their claim to the test as to what would take place. You know what I'm saying?
Exactly. I've always said that a pendulum, a mechanical gyro compass, and a laser one. Yeah, exactly. Yep. And the reason for the gyro compasses and not the magnetic one is, like Napalm said, because in the olden days they had the wooden boats, it wasn't a problem. But when they made the metal boats, the compass reading was off because of the metal. So that's why They made the gyro compass, which doesn't rely on magnetism.
I was beginning to think they made it solely to prove globularity and spin, but I'm suspicious.
Yeah, I remember Bob the Science Guy. I don't know if you guys know that. Bob the Science Guy, this dude brought it out years ago as proof.
Well, I know it's in all the manuals, and when you look on the internet for like anything about Earth spin, the first thing you're served is like a whole heap of that. So
Yeah, you can find mountains and mountains, and they'll tell you, "Look, you're dumb. Look at the manual, right?" Like they say with the Coriolis. Look, the manual says they have to adjust for the cannonball, right? Yeah.
All right, I'm back.
Yo,
Sweet.
welcome back.
Well, they told me this thing can only work on a globe, therefore it's a globe because it's working. Case closed.
That's it. Yeah,
Got
yeah.
it.
Now the ring laser one, right? What's the claim? What the claim that it picks up motion due to what? Due to the Sagnac effect? What's the official claim of that one?
So for the official claim, they say they invoke a time difference between two observers, one hypothetical, one at the one at the recorder. They say that the rotation difference produces a time difference between the two, and like the speed of light difference like is an illusion between them, and that's what's producing that's what's
Oh my God.
not producing the fringe.
Everything's an illusion. I forgot that's how they
Wow,
live.
man.
Yeah. So yeah.
But the mechanical gyroscope, it detects motion, they say, right? Or it well, let's just say, let's start off with the with just the gyroscope, not the gyro compass, right? The gyroscope, the mechanical one, keeps its rigidity, and the Earth underneath spins, right? What's the claim with the laser one? The same thing.
Yeah, they
The
say
official
that
claim.
Yeah, they say that it picks up Earth's rotation with respect to Earth's axis, the center of Earth's center of the geoid.
Well, they
So
invoke the
what
magnetic
is
field,
spinning?
though. They invoke the magnetic field to make it work.
Well, for
Okay.
Michelson Gale, like for a ring laser, though, different mechanism.
Oh.
That's where they invoke the
Yeah,
time
that's what I'm
difference
saying.
between
Yeah.
the two observers. Yeah,
So what do
so
they
they
say
give
the
two different
mechanism is?
mechanisms for the same phenomenon.
Yeah, literally.
Dude, they're so wild, bro. Sorry, sorry. What was your question, Nessie?
Because it's indifferent, right? So what's the claim of the ring laser? What does the ring laser pick up? The ring laser gyroscope. What does that pick up? What's the official claim?
The official claim it picks up rotation with respect to the center of Earth's axis of rotation.
So it's picking up the platform rotating, or it's picking up, what is it
Yes,
picking up exactly? The
that
platform
that's
rotation.
their claim. Yes, that's their claim. Well, I mean that's what it does. That's what it detects. But yeah, they're saying that the Earth is the platform in this scenario, and it's detecting the rotational rate of the Earth relative to the latitude.
Okay, gotcha. Right. So they're not saying they're picking up anything um any interference, because I'm trying to figure out what's interfering if the bottom is spinning, right? What fringe is interfering? Is
Well,
the spinning platform itself what's picking up
yeah,
the fringe?
dude, that's a really good question because it's like when they have an airplane that takes off and it's in its own reference frame or whatever they say, the Earth's rotating under it, and it's like they actually are saying that like it detects that. Crazy.
So what the heck, man?
Yeah.
Yeah, that's something. Yeah, like the mechanical one, I get it, right? It's keeping its rigidity. There's a plate on the bottom, right? There's markings on it, and they say, well, it's keeping its rigidity, and the bottom and the bottom is turning. The Earth is turning, just like they say with the pendulum, right? Pendulum swings back and forth. And a lot of ballers think that the pendulum processes. That's what a joke that is. But anyways, and the Earth turns underneath, right?
Yep. Yeah.
I got to look more into this ring laser one. I haven't really looked into it.
Yeah, it's pretty interesting. I just did like 45 minutes on it, just kind of reading from the manual and summarizing like their explanation of how they try to explain in the effect that they're measuring as a relativistic effect. Because they got to keep the speed of light the same. So they give like an explanation in there. So I just like read it right from the manual and then just kind of went over different aspects of it and how it works.
Yeah, too bad I missed that. So let me just get one thing straight. The detection part, the laser interferometer part, that's on the base of the machine.
Yes. Yep. Yeah. Actually, I can walk you through a little bit of it. No problem. Let me pull up. I'm screen sharing now.
So let me get in. Okay, good.
Yep. So let's see here. So I don't have. So you can't really tell from this diagram because this looks like a computer. But what the apparatus looks like a simple form here. Hold on. Let me scroll down to infinity real quick. Grief. Almost there, I swear.
No rush, bro.
All right. Whew, here we go. Okay, so if you have this circle here, say this disc is a platform, and then you have 4 mirrors placed on it, and then you have a light source, and then the beam gets split by the mirrors, gets reflected around in a loop, clockwise and counterclockwise, and then it returns where it started. And on that return mirror, it's half silvered, so it recombines on that trip back, and then it hits a photographic plate. So the whole apparatus is constructed on the rotating platform, so it's all within the same rotating platform, essentially. To answer your question, yes.
Gotcha. So one beam is going one way, the other beam is going the other way, correct?
Yep. Fired from the same
that's what
source.
Okay, got it. That's what I thought. Okay. But the main thing was if it's on the same platform, so it's on the base,
Yeah, so while this is rotating, it will detect its own rotation. And then in addition to that, like if there's so say you attach this to like an aircraft or something and it's, banking or whatever, it will detect that additional velocity. There will be an additional variance added to the in a sense, it's basically like a velocity addition, to be honest with you. So like however fast this is rotating, it's going to produce a fringe shift pattern proportional to that rotation.
Yeah.
Yep. So then when it's attached to an airplane or whatever, and then that banks, that velocity is going to get added to that, and it's going to cause a further displacement in the fringe. And they take the difference in that, and they go, okay, we're going at 700 miles an hour or what have you, right?
Right. Gotcha. Mm-hmm. So
then
in
they
the
have
plane, though, in the plane, that they don't say that it can detect the Earth rotation, do they?
They say that when it's on the ground, it does, and then it detects it at altitude, but they say that it detects it at the same what do you call it? At the same 15-degree rate. That there's no change.
No way.
Xena kept telling me that
detects it in the air.
Xena kept saying that the ether wind should blow them out of the air. Not really, but he kept saying that like it should detect them every time they get up. It goes. It doesn't get. I'm like, so you're gonna say that like a fraction of a nanometer worth of a fringe is gonna push a 747 off course? Okay, whatever. But he said it like 150 times.
Yep, same to me.
Yeah. Nice.
Yeah, but think about it. If it's in the air, how is it going to detect the motion of the Earth?
Dude, it's that's a whole other issue, right? But like,
dude, that's what always perplexed me. But it's like, okay, what have you? Like, we'll go with that.
We're rocking the motion of the sky from the ground, so I'm not going to push that.
That's an Achilles heel right there. Right there, looking at it for like a couple of minutes, I found like, what, are they serious?
Yeah. Well, the fact that the gradient gets stronger when you get higher, directly falsifies the geometry of the relationship where they say it's due to the cause of the Earth rotating.
They don't even know that. They don't even know. They don't even know that that's bad or that impossible. Like the physical impossibility of that escapes them, dude.
Yeah, like when
Yeah.
they say thanks Bob, right? Like they don't
Yeah,
understand
dude,
what they're saying. Yeah.
they have no idea. So the same equations that they thank Bob with that derive a proportional velocity based on velocity, right? Those same equations were linearized in 2004 experimentally. So all the all the all the attempts to measure Earth's orbital velocity using Michelson-Morley using a different type of setup for interferometer, it was actually shown that those velocity readings are completely valid. So the 6 kilometers a second that was shown, the 8 to 10 kilometer fluctuation in altitude that Miller got, that was corroborated by Galev. That was also the same fluctuations were measured by Monera over a course of 3 years. So when you get into all that, there's just so much evidence that the speed of light changes.
Absolutely, but think of the
Proportional to a
implications.
velocity, proportional to a velocity that they can't work with.
Depend on. Oh,
Yeah, no, they depend on 30 kilometers a second, and it measures not that at
Oh,
all.
I thought you meant the
So
proportional velocity portion of the range measurement equation.
no, dude, we were talking about
I know.
interferometer
I
measurements.
know.
Just black out.
Yep.
Nice. Okay.
And then defended myself roughly.
Hell yeah. That's what's
So
up.
some
But it
implications, right? Bob's thing is on the ground, right? Albeit at higher elevations, but
Yeah.
this plane claim, think of that. That's an Achilles heel. That goes to you guys, the ether boys, right? If there's a rotation in a plane, well, that can't be Earth curve, right? It's got to be something
well,
else.
Well, they would say that it's uniformly 15 degrees per hour, and then that's where we would get into the specifics of how the device works, how it takes measurements, how how they're determining what a 15 degree per hour shift is, versus all the contributing factors that actually make it go above 15 degrees per hour. Like how they're zeroing that out is kind of like what we're finding out is like a huge portion of the situation, because it takes like millions of readings a second. It puts out an insane data set. It's constantly fluctuating in temperature. So and because of the nature of the measurements being so precise, the little fluctuations in temperature are producing, readings that have to be, or errors in the readings that have to be compensated for. So it's like there's all these corrections and algorithms that are built into this device that we can't even really analyze or determine like what's going in on the back end of it. We just kind of have the surface level narrative that they give us of all the corrections that make sense within the confines of like, hey, nothing going on here, guys. Just trying to get this device to work. Nothing weird going on here. But it's like just within what they did to get that to work, it already provides enough mechanisms for there to be a deception where they have an actual true coordinate system, and they have all these people navigating and referencing a coordinate system that's not actually related to the quote unquote true coordinate system, which is hidden through the analysis of these algorithms where it can place you on that coordinate system, that reference coordinate system, and make you think that you're on a geoid instead.
Only with the perpendicular downward direction relationship to gravity, of course.
Yeah, with respect to your perpendicular relationship to the gravitational potential of the geoid,
right?
Of your choosing.
Do you know what Zanuck said? One of the things I just remember that he's like, I had to have a personal toroidal personal toroid, I think is what he came out with, and I was like, yeah,
nice.
Sure, we'll just go with that. That works.
Nice. I mean, he does have a personal toroid. I'm glad he's accepting it.
Well, he understands that when he goes to get the truth, he has to adopt that immediately, right?
Yeah. Dude, I thought that was really funny too. He was like, "Then it's all true," and then it's a toroid. You were like, "Yeah, but let's come back to that in a minute."
Like, yeah, wait a second.
Like nice psychoanalyzing. I'm like, really interesting. You went to toroid,
right? You're not going to try and plug the hole in the boat. You're going to blow up the whole thing. Okay. I mean, then you must know how shitty it is, right? Like,
it's like, tell me about this toroid you guys got.
Yeah.
But this plane thing, like this is a big thing. If they're claiming that on a plane, if they claim it still detects Earth rotation, like that's a big problem. That's a big no-no right there. What is it detecting? It's not on the ground.
If it kept it at the same speed, they would just invoke their differential between the hypothetical observer at the at the at the center of axis, dude. I know what you're thinking. Like, dude, it's a body bet. Like, dude, they don't like they've
They don't
already
care.
tricked everyone, and like it's over. Like for that.
It's one of the
And,
pseudo
and then
forces.
yeah, and then on top of that, we wouldn't know the variance in a plane anyway because we can't analyze it, and it's already going to give readouts that correspond to what it needs to put them on a geoid that's rotating at 15 degrees per hour. So it'll never output that in their readings. Like it might be in the raw data, but then it's like, how are we going to extrapolate the raw data to show like this is where the barometric pressure affected, this one's where the temperature affected it, and this one right here was your boy ether drift and the velocity. It's like that's like I don't know how we could do that. Seems to be the issue, and the issue for them too, because like they don't even get a 15 degree. It gets averaged out and rounded down to it. They're just told a story and it goes along with their world belief, so they go along thanking Bob and not understanding how the technology even works to begin with.
Of course.
Which
It's on
isn't
the
even
internet.
necessarily their fault because it comes with a manual that tells them like it works a specific way that's in alignment with relativity, and they don't even like a lot of work has gone into making the Sagnac effect appear to be a relativistic effect to continue this deception. So
It's true.
not
Well,
trying
that's
to put
probably a
anyone down.
pretty good wrap up summary to close out a stream on if you want, unless we got more to go on.
No, I think that was pretty much everything, man. Thanks everyone for stopping by. It's been awesome to present these and go through everything, and the communities. It's awesome to have people reaching out like, hey, I'm reading this book on Maurice Elias or what have you. It's just been really cool.
For real. Yeah, it's really cool to hear people like other people doing research alongside us and sending us things to share and to share with you guys, to share with other people. It's it's really fantastic. Almost kind of surreal.
Yeah.
Right? Remember when we were on the other side not too long ago?
No,
It's like seemed like forever ago.
True.
seems like only yesteryear. All right, boys, I'm gonna go ahead and close it out here, and we'll pick it up on Flat Earth Friday.
Hell
Take
yeah.
care, y'all.